Okay, so just before the break, right, I guess we saw this simple solution. We're basically just going to build this CountMin structure with this epsilon half precision and failure probability 1 over u squared. Just going to loop through the whole universe and query every single item for an estimate and put the ones the output where the estimates are at least epsilon times 1. Right. And this was great except for the query time, which was this u log u. It's very awful. It's going to take way too long time. The space usage, one can show that this is optimal. I guess an update time of log u is also very fast. And I guess there are also lower bounds saying something like square root log u is lower. So this is the update time is close to optimal. So okay, good. But now we're going to try and improve the query time. We're first going to see, I guess, the original solution for improving it, and then we're going to see in. So I think we'll get rid of this part here. Okay, so we're still gonna build on the CountMin structure and use this as a building block. We're gonna try to do it in a more clever way to avoid this huge query time overhead. Let's see. So what we're going to do is we're going to imagine. This is just for kind of like our understanding of what's happening. We're gonna imagine now that there's a binary tree on top of the universe so that the leaves of this tree correspond to the universe elements. And so basically, which let's say that the universe is universe size is a power of 2 to the half of some r integer r. And so in the leaves, this is where we imagine the universe elements. So like the first leaf is just stores the frequency of 0, this stores the frequency of 1, the frequency of 2, up to the frequency of 7 in this case. Okay. So let's assume we have this tree, and in each of the levels above, let's say we have an internal node in this tree, let's say this node B here. We also imagine that there's a frequency for this node B. Maybe we can call it GV. And the frequency of V is just the sum of the frequencies in the subtree. So GV, in this case here, this frequency here is just, put it out here, is F0 plus F1 plus F2 plus F3. So it's the sum of the frequencies in the subtree. Like a binary tree where every node is just storing the sum of everything in the subtree. Okay, so this tree here, just here at the bottom, all these frequencies, the bottom, this is basically the original frequency vector F. Right? You can also, so this is on a universe size U. You can also imagine all the nodes in the level above. You can also think of it as a frequency vector itself, just half as long as the one the leaves. So here's another frequency vector. Maybe we can call this one at level 0. This is the frequency vector at level 1. Up here, there's a frequency vector at level 2. At the top here, there's a frequency vector at level log 2 of u. Make sense? So we have these frequency vectors. Every frequency vector just contains the frequencies of all the nodes in this level of the tree. And every node in the tree has a frequency that's the sum, the frequencies of all the leaves in the subtree. So maybe, I guess it's, I don't know, if we have a slightly smaller universe size 4, maybe this is frequency 0, 2, 1, 3. And this would have a frequency of 4, this would have a frequency of 2, this would have a frequency of 6. Right? So the first frequency vector also here is the vector 0, 2, 1, 3. This is the vector 2, 4, and this is the vector 6. So with this representation in mind, we want to try and solve this heavy hitters problem. maybe for now, let us just to start out with, let's assume that we actually have stored this entire tree. And of course, that's way too much memory, right? It's going to use u log u, or maybe u, 2u nodes in total, so it's going to use a lot of memory. So I wanted to say here, call this one f superscript 0 for frequency vector, and stores everything here. This f superscript 1 is a vector with these 4 entries, and f superscript 2 is a vector with these 2 entries. So I can kind of do, maybe write f ij to denote the jth entry of the frequency vector for level I, for I levels above the leaves. This is kind of the notation. So for now, let's assume that we actually stored this tree, okay, with all these frequencies in them. And let's try to see how could we then produce this list of heavy hitters in an efficient way, like how, in terms of runtime, how could we quickly find all the heavy hitters? So let's try to do a list heavy hitters procedure here. List heavy hitters, and maybe I want to actually do it as a recursive procedure. So let's say this recursive procedure, let's say it takes in a list L that is initialized as empty, and it can add elements to this list. And then let's say it takes a level. Let's say the level is I. And let's say it takes a node in that level, which is J. Let's say I want to give now a recursive procedure that is going to add to L everything in the subtree rooted at the node in level I with index J. So I'm going to go to level I, and I'm going to go to the node whose index is J, and I want to create a procedure now that lists all the heavy elements in this subtree. Because if I had such a recursive procedure, then I could call it to begin with. I could kind of list, and then I'm going to do L, and then I'm going to do what is the level? It's log U, and what is the node? It's the root. Right. So this call, the L will be the empty list. Sorry, so I'm just going to start out with an empty list. I'm going to start out at the root level at node number 0, so that's the root. And then this procedure is going to output all the heavy elements in the whole tree. So let's say I want to try and do a procedure that traverses this tree to find the heavy elements. And the way it's going to do it is it's going to examine these frequencies that we have inside the tree. That's the kind of idea. We want to look at these frequencies to determine in which parts of the tree should we recurse. Make sense? Okay, so we're currently at some node at height I or at level I, and its number is J on this level. So intuitively, what we'd like to do now, if we're in some node, is we would like to perhaps recurse into the left child and perhaps recurse into the right child to produce some output. Make sense? We just want to see, should I recurse into this left child and should I recurse into this right child? So to figure that out, let's start by computing index of the left child and the index of the right child. Let's try and see if we can give a formula. So let's say the left child, what is the index of the left child level below? Maybe one can kind of pattern match and say, okay, maybe this is number 0, this is number 1. What are the indices of its children? It's 0, 1, it's 2 and 3. So I'm just going to write out what these two are. Maybe the easiest thing is to just try and look and see that this looks correct. Maybe if you see these presentations of the binary heap in introduction to algorithms, it's also this way that you can compute the root for the children of the node in the binary heap. So here, try and see, maybe just pattern match a few times. This has index 1 in this level, 0, number 1, and its children are 2 and 3. That's also what we get from this formula. Then you can say, well, okay, this is number 1 in this level. Its children are 2 and 3 in the next level, so that also matches. Yes, this one is number 2 in its level, and this formula is saying then 4 and 5, which is good. This is just 2 formulas to compute the indices of your children. Then I guess we have to, first of all, we have to check, maybe we should have done that first, but let's do it here. If we are already at the leaves by 0, we have actually recursed all the way down to the leaf. Then what we want to do is we're just going to add this kind of like a simple procedure. So if I end up in the leaf, I'm going to just this, and now if I'm not in the leaf, I'm somewhere in an internal level of the tree. I'd like to recurse down the tree, but of course I want to be efficient. I don't want to visit the whole tree. And so maybe I'm going to do something like list heavy hitters, send the list L as an argument. I'm going to go to the level below, and I'm going to go to the left child. I'm also going to do the same with the right child. Level below, right child. But could I do a check here so that will kind of prevent me from spending a lot of time? So what could I check if I don't want to recurse in here unless it might be necessary? Say I have all these frequency vectors up there. This is some check I could do. Let's recall we're in the strict turnstile bottom, so all frequencies are negative. This is some check I could do to make sure. To remember again, right? We have to find all the ones whose frequency is at least epsilon times the 1 norm, and no one whose frequency is less than epsilon half times the 1. Let's say I know what the 1 norm is. Okay?
You know the sum of the on the garden node?
Do I know the sum of the leaves of the current node? I could check it, right? Let's say that's the frequency. Yeah. So I could try and check that one. Yes. Yeah. So if, right? So if, okay. So let me check. Actually, I'm going to do it for the left child instead. So I'm going to check the frequency of the left child. That's the frequency vector in the level below, and it was the left child. And I'm going to check if this is at least. Actually, I'm going to change it slightly. I'm going to say at least epsilon times the 1 norm, because we never underestimate. So it's enough to do this check. So if this, then we recurse into the left child. And similarly, if the frequency of the right child is at least epsilon times the 1 norm, we're going to recurse into the right child. Oh. Let's try to maybe analyze this recursive procedure first, just see what happens. So first of all, we have to argue that we will always output all the heavy elements, right? So why is this the case? Well, because if some element is heavy, like in this binary tree, if this node is heavy, meaning its frequency is at least epsilon times the 1 norm of the vector f, then because this is the sum of all the frequencies and all the frequencies are non-negative, that frequency is also at least epsilon times the 1 norm, right? And this one is at least epsilon times the 1 norm, and that one is at least epsilon times the 1 norm. So everyone on this route to leaf path is at least epsilon times the 1 norm, which means I will indeed follow this path, right? Because I'm checking. This check will always succeed on the whole path down to the heavy elements. Okay, so there could, of course, also be, because I'm summing up some stuff, there could also be some nodes that look like they're heavy, but actually there are no heavy leaves in the subtree, and then it might stop at some point. Right. Secondly, we have to check that we don't put anyone in there who's light, but that's the case because we would never put a light element. If this one is light, then when we add the parent and we ask, is this frequency at least epsilon times the 1 norm, that would be not going to risk putting it. So indeed, this actually produces a valid output. The question is how much this tree are we visiting when we're doing this? Like how many nodes will we see? with this procedure. Could we risk, because we could have these nodes that look heavy, but it's only because we sum up some light nodes in the subtree that could visit more stuff than just things on a path down to a heavy element. So to analyze that, what we'd like to do is we'd like to try and relate these frequency vectors for the different levels. In particular, we would like to, so it's the frequency vector at the 0 level, that's just the full frequency vector, right? That's the original frequency vector. How does this, the one norm of the frequency vector down here relate to the one norms above? Of the levels above? Is there any relationship between, say, one norm of this frequency vector and one of these? Smaller than, greater than, what do we have? Any, yeah?
Always greater.
It's always great. Yeah, can we be even, yeah, and why?
Some, and we know the frequency in the it'll be.
Yes. So can we even do even something even stronger than it's greater than 2? That's greater than or equal to. Say something more. Yeah. It's equal. Yes, exactly. It's actually equal to it, right? Because it's just the sum of every node is the sum of everything. The one norm is the sum of all the entries. There's nothing that cancels out. So they're actually equal. They're equal all the way up. That's one nice observation. Like the sum of all the frequencies of the level is the same for all the levels. Plus we're in the strict turnstile. That's one here. Okay. Now the question is the number of nodes that we visit in this recursive procedure. Are we only going to visit a node if its frequency is at least epsilon times the one norm of that, right? This is the only time we visit a node. The question is, these are the nodes that I read here. The question is, how many of these nodes can we before we finish? So the question is, how many of such nodes can there be in one level? Each and every one of them must have a frequency of at least epsilon times the one norm. So can we say something about how many, it's upper bound on how many? They all be heavy somewhere, like all the levels. Okay, we're going to use this observation here. How many can make up an epsilon fraction of one norm? Yeah.
1 over epsilon.
At most 1 over epsilon of them, right? Because in particular, if there are k red nodes, then it must be the case because the one norm is the sum of all the frequencies. And then this has to be at least k times these. At least each and every one of them is at least epsilon times the one norm. And if there are k of them, then the whole norm has to be at least k times epsilon times one norm. And this one here was equal to. So if you rearrange, see k is less than equal to 1 over epsilon. It can only be 1 over epsilon in any level of these red nodes. So the total number of these heavy nodes, the red nodes, well, there's 1 over epsilon in each level, and there's log u plus 1 levels. Okay. So not very many. And in particular, this is basically the query time, right, of the time for this procedure. Because we're only ever visiting these nodes that have such a frequency. We do constant work for each of them. Does this make sense? So this, if we had this tree, then we could find all the heavy hitters in 1 over epsilon log u time. much better than u log u. Particularly, the size of the output is basically 1 over epsilon. It could be there could be 1 over epsilon heavy elements, and we're going to pay 1 over epsilon log u. So it's very fast to produce. Okay. Now, okay, of course, we don't have this structure because this would require storing this whole tree, and the number of nodes in this tree is, well, there's u plus u half plus u quarter, so like the 2u nodes basically in this tree. The space usage would be proportional to the universe size. It's too much, right? So, but because we want to use sublinear space. Okay, so what do you think we do with this tree? What do you think is the idea? What could make sense? There are some frequency vectors, I guess. What can we do with frequency vectors? We don't want to store all of them. So we want to use sublinear memory to store vector frequencies. What do we have of solutions for that? And what are we doing with it? We're basically asking for what is the frequency of this element, what is the frequency of that element. We store CountMin structures, right? Whereas they can store a frequency vector and they can estimate the values of the entries. So that's what we're going to do. We are going to store a CountMin structure each level of this tree, which is we're going to store log u plus 1. I guess we actually don't. I guess we never need the top one, but we're going to store. So we're going to store log u frequency vectors. Let's try and do that. So that's what we're going to do. So we're going to modify this in a second. So let me erase something else. Let's go over here. So what we're going to do is we're going to store CountMin 0 up to CountMin log u. Say -1 is sufficient. We're going to store these CountMin structures, one for every level of the tree. So CountMin of I is supposed to represent the ith level of this tree, the ith frequency vector. So this one is going to So CMI is going to approximate the ith frequency vector. That's the idea. So now I'm just going to tell you what parameters we're going to set. We're going to set in all of them. We're going to set epsilon half and 1 over u squared like we did before in the slow solution. So these are the value that these are the parameters that we're going to initialize all these CountMin structures with. So this solution here that we're going to see here is due to Graham Cormode and Muthukrishnan. So we're going to store all these CountMin structures, one for every level, representing these frequency vectors. And let's say now we want to see how should we update them, right? Because now we're in the streaming setting, and we get an update for an element I, the frequency change of delta. So if we think about this tree here, right? What happens if I'm going to update element I down here? That means I should add, how is this tree updated? Every node stores the sum of everything in the subtree, right? So that means I should add delta to this node, to this node, to this node, and to that node. Does that make sense? So that's exactly the change to the tree. Add delta to everything on the root to leaf path. The question is, what are the indices of these elements on the root to leaf path? Maybe actually let me call this j. So I is the level of the tree, j is the element being updated. So I want to loop over all the levels of the tree for I equals 0 to, I guess we're just ignoring the very top log u minus 1. I want to now update the CountMin structure representing level I, and I want to update, and I want to do the update is I. What index should I update? So I guess if this is my J, I just want to figure out what is the index of the parent I levels above, ancestor I levels above. I'm just going to write down, you can convince yourself of this. You just take your J and do an into the division by 2 to the I. Divide by 2 to the I, round down. That's the index of your ancestor. And okay, actually, if you wanted to code this is super simple, and this is just a bit shift by I positions, right? So it's very fast to implement this. So this is the whole code. If you already have a CountMin implemented, you just update like this. That was easy. So that's the update procedure. Now let's see if we can also do the modify the query procedure over here so that it works. So we're going to kind of simulate, kind of do the same. We're still going to call it the empty list and root node of the tree. And I'm just going to swap the order now a little bit more natural. If we're already at the bottom, just going to add I to L. Similar to, otherwise, we're internal, and I guess return. And then we're going to say left child is 2 times J, the right child is 2 times J plus 1. And now we would like to do these checks to see if we should recurse into the left child and the right child. But now we don't have the actual frequency vector, right? Before we would check the frequency of the left child, we check the frequency of the right child. Now we're not storing them explicitly, so what do you think we should do now? What do you think is a good idea? Before we check them explicitly, now we're not storing it, we're storing something else. So before we explicitly looked, recall, before we looked at this fi minus 1 L, now we don't have fi minus 1 stored explicitly, but what could we do instead? How are we representing the frequency vector? Yes, then we're going to just do CountMin in level I minus 1. That's representing frequency level I minus 1. And it's element L, so we just say, well, let me estimate L. And if this, so if you remember again, the CountMin never underestimates, and we just want to make sure that we will eventually reach all the heavy elements. So we're just still going to check like before, is this at least epsilon times the 1 knob? Then we're going to curse, just heavy hitters, L, I minus 1, left child, and similarly, if CountMin I minus 1 dot estimate of right child, then we're gonna cursively call this the heavy hitters, left child, layer I minus 1 R. Make sense? This is basically the same kind of query procedure as we had before, except that we're now using the CountMin sketches to decide whether to recurse into these leaves or not, or these children. Of course, we now have to argue for correctness for this procedure. And it gets a little bit more complicated, but the correctness is actually easy, right? We've got one part of the correctness. We have 2 things to check, right? We have, number 1 is every element that is heavy, is it in the output list, right? Is every element whose frequency is at least epsilon times the 1 norm, would that be in the output? By the same argument as before, if this node's frequency is at least epsilon times the 1 norm, then that's the case. Every node along this root to leaf path comes up something, and it's strict turnstile, so it can only be even bigger. and the one norms are the same across all the levels. So that's true. So and we never underestimate. That's also this part here, right? We never underestimate, which means we will always follow the paths that lead down to the heavy elements. So we'll always put all the heavy elements in the output. Then the second part is, what about light elements? Would we risk adding a light element to the output list? This is what we have to try and analyze now. Could it be that we add some light elements to the output in this way? And it turns out we have already basically done the analysis when we looked at the really silly solution over here. And remember, the silly solution, we just queried everything in the universe, define an event for every one of them, and check would this be overestimated by too much. So let's see again if we can actually do something similar. So the observation is, if I have a light element, someone that I'm not allowed to add to the output, it's sitting in, let's say, this node here, F0, element 0. If this one is light and I'm not allowed to add it to the output, if I am to actually put it into my output list, then what can I conclude? I can conclude that the CountMin structure that if I ever reach the parent, right, and the parent then queries the CountMin structure at level 0 for my frequency, right? So the parent here would query for my frequency. That estimate has to be way off, right? Because I am light, I'm less than epsilon half times the 1 norm, and the only way I recurse into this node is if I estimate it to be at least epsilon times the 1 norm. Does that make sense? The only way I could ever visit this node, if it's a light node, is if I was in this parent, I made an estimate here. It looks like it's heavy. It looks like it's epsilon times the 1 norm, but I know this is a light element. It's too light, right? So I must have overestimated by a lot. I must have overestimated by more than epsilon half times the 1 norm, right? But that is a failure, right? Because I set the precision of these CountMin structures. So the only way this can happen is it's going to be a failure if this happens. So what I'm going to do now is I'm basically going to define a bad event for every light element. It's basically going to say CountMin of 0 dot estimate of I is greater than frequency of I plus epsilon half times the 1 norm. Make sense? Because I can only ever, if this event doesn't happen, then I cannot visit this node. Right? Make sense? So the analysis is the same. I can use the union bound because I know I can never, if none of these events happen, I will not put anything in the output that I'm not allowed. So by the union bound, the probability that there's at least one element who is overestimated by more than epsilon half times the 1 norm is no more than the sum of the probabilities. And I indeed set these failures to 1 over u squared. It's the same computation before, and my failure probability is both 1 over u. Does that make sense? Okay, so that was the correctness. We have the correctness procedure. We know what the update looks like. Maybe you can see what is the time and the space. So the space usage. So what do I have? I have log u CountMin structures with epsilon half and 1 over u squared. Right? So the space usage is, well, there's log u of these structures. They all take order 1 over epsilon log u space, because there's this log of u squared is just 2 log u. So this is like 1 over epsilon times the square of the log. So let me write like the log squared of u. It's the square of the log, not the log of the square. Log u times log u. So that's the space usage. It is, remember the silly solution the one where we just queried everything in the universe had 1 epsilon log u. So it's almost as good, but it's a log u factor worse. The update time well, the update procedure tells us to log u times make an update on a CountMin structure with a failure probability of 1 over u squared. CountMin structure have this update time of log 1 over failure probability, so that's log u times log u. The update time is log squared of u. So for every level of this structure, we have to update a CountMin structure with that has an update time of log u. Then let's finally the query time to produce this list. And let's try and see if we can analyze that. Perfect on time. So let's do that. Maybe let's do it here. Okay, so how do we bound the update time, right? As we saw before we introduced these CountMin structures, what we argued was that we're not going to visit very many nodes in this tree, right? And basically that's what we're going to try and do again, because we can see here in this query procedure, right? For every node that we visit, we're going to do 2 queries to a CountMin structure. And those 2 queries, that's going to cost log u. It's log u, right? So the total time is going to be log u times the number of nodes that we visit. Which is going to cost 2 log u. So we want to bound how many nodes are we going to visit in this tree. How many nodes are we going to visit? So similarly to before, like what we did before when we had these exact counts, we argued that we would only ever visit these heavy nodes, right? The ones whose frequency is at least epsilon times the 1 norm. Now we're not looking at exact frequencies, but we're using these estimates based on the CountMin structures. So we cannot do exactly that. So what we're going to do now is let's call, so we say a node in this tree is, we say that V is heavy. V is some node in here. Let's say GV is the count, so this is like some frequency of some node, depending on, like it's the jth node on level I. If, let's call it heavy, if it's frequency, so the sum of everything in the subtree, in this time I'm going to say it's at least epsilon half times the 1 norm. So it's slightly different than before. Before we said it's at least epsilon times the 1 norm, now I'm going to say epsilon half times the 1 norm. So that's a heavy node. So we have this tree. All the nodes that I colored red here are the heavy nodes. So maybe we can start by asking how many heavy nodes are there in the tree? Can we give an upper bound on the number of heavy nodes? Maybe first in one particular level. I guess it's the same argument as before almost. So how many heavy nodes can there be in one level when a node is heavy, when it makes up epsilon half times the 1 norm? Yeah.
2 over epsilon.
2 over epsilon at most, right? Because if there are more than, because the 1 norm in any level is still the 1 norm of the original frequency vector. So the number of heavy nodes is per level is at most 2 over epsilon, and the total number of levels, this is log u plus 1. This is the number of heavy nodes. The rest are light. So now what we'd like to argue now is, with good probability, we are never going to visit a light node. Now I'm going to define an event for every node in this tree that is not a light node. Let's call it EV is an event. And this is going to visit V, and we're going to have, so, and then we have, what is the probability that we ever visit a single, such that V is light, Right, so the probability that you ever visit a single light node is at most the sum by the union bound over all the light nodes. Then we bound the probability that we visit a light node. So here's some light node V. What can we say about the probability that we visit V? So V is light, meaning its frequency is less than epsilon half times the 1 norm. What has to happen for us to visit this node? How could we end up visiting this node? Right, so we must have made an estimate of its frequency at some point, and particularly its parent. We must have gotten to the parent and then queried the CountMin structure for its level to get its estimate of its frequency. And that estimate must have looked like the frequency was at least epsilon times the 1 norm. But we know this is a light node, so it is less than epsilon half times the 1 norm. So it's indeed an error in our estimations because of this choice of epsilon half here. So this probability is at most 1 over u squared. So this is at most the number of light nodes in the tree. Well, there's at most u plus u half plus u quarter. So there's most 2u times 1 over u squared such nodes. So this is like 2 over u. So the probability we ever visit a light node is at most 2 over u. So now we can say, okay, if I don't visit any light nodes, then I know I'm only visiting heavy nodes. And there are not very many heavy nodes. There's only 2 over epsilon log u heavy nodes. Each of them is going to cost me log u time here and here. So then the query time is going to be 1 over epsilon log squared of u, right? With probability 1 minus 2 over u. We can get rid of this with probability 1 minus 2 over u. The simple trick is to say, okay, if I ever visit more than this number of nodes, I just abort that thing. I just say, okay, if I ever, during my recursive procedure, if I ever saw more than this many nodes, I just abort. This adds 2 over u to the error probability, which is already like 1 over u. So then we're not gonna, this is just, we can just put it in the failure probability, right? So this is just, you can actually have this always, the query time is worst case, 1 over epsilon log squared of u. Worst case. By simply checking if we ever saw too much, then we just, makes sense? So this is this full solution here, and I think this is a good time for another break. Let's 7 thing.